Hello and warm welcome to everyone. So today will be the last lecture of the week 7 where we'll demonstrate, we will see how we can use R to implement the multivariate time series analysis. So in the last few classes we have discussed about the vector autoregression, we have discussed about the VECM, we have discussed about the contegration and VECM. So how we will be using those methods to analyze our data. So for that, as usual, the last classes, I am using here a project folder where we have kept everything. So you know that to open the project folder, we have to click on the project icon. So if I am clicking here the project icon, it will open the R Studio. So through which basically we will be estimating these models. So here you can observe this. Here we have no data, nothing is there, and this is we have the 3. So this is, this is console, and here we have the data. Now here you can see we have the script file. So a script file where basically we have written all the codes needed to estimate those or execute those models. So once we click on that, so it will be open. So if we click here, then you can see here we are opening. So last few classes we have discussed that these are the packages we are using. So here basically 2 new packages we have. One we are having the variance for the estimation of the vector autoregression. Another we have variance for the estimation of the structural vector autoregression. Once you open the script file, if any of the packages is not installed in your system, then here we get the message. For example, here we are getting the packages variance and variance required but not installed. So to install that we can click here, or we can uncomment this. So if we remove this, then we can see it is active now. So now if you execute this, then it will be automatically installed. Or here you can say directly click install, then it will be installed. So if you see that we have clicked, so here you are getting that stop button, right? That means it is installing. So once it will be installed, then here we will have the message it has been installed. So here you can see that we have already, it has been installed. So here we are. Now once we install, then in every session what we have to call that particular package to use that. So to make it active, we have to use the function library. So we have here library, variance, variance, all those we have. So let us execute one by one. So either you can click it here, run and keep the cursor here, or keep the cursor there. We can use the keyboard, that is the control plus enter. So you can see here, so all those has been attached here. So let us see here we have. So we called everyone, we have attached every packages here. Now obviously the first thing what we have to do, we have to import the data. So again here the function of that is data read Excel. So basically that means we are using the function read underscore Excel to import the data. So here the data file is this, and you know that the data file has to be written with the extension. And here the column types, basically see here we are referring that the first column is of the date, second column is the nature of that is the numeric, that is the data, the numerical form, the second is also numerical form, and third is also numerical form. And I am storing that imported data into the data. So imported data has been stored here by the name of data, where D is the capital. So let us execute this. Here once we execute this, you can observe here what we have. We have a new object which has been created into this global environment, this data. If you click here on the radio button, so what we can, it will expand and it will show what are the first column, second column, and third column, and the fourth column we have. So here we can see in the first column we have the time 1, so the name of this, or we can use the command view, so to see the data structure here. Remember, in view what we have, the V is the capital. So if we enter here, so here it will open a new window here. So here we have 4 columns. The first column's name is time 1, second column's name is BSE, third column's name is WCMR, and fourth column we have CPI. So first column is basically nothing but the time. Second column is BSE, is basically the price, closing prices of BSE 100, and the third column is WCMR, that is weighted call money rate, and the fourth one CPI, that is the consumer price index. All three data has been taken from the RBI, that is on the web from the database of the Reserve Bank of India. Once we do that, it is always better to examine the data what we have imported. In the time series, the first thing we should be very critical, specific about, or very careful about the presence of the missing observation. If we have missing observation, then then we will not be able to use the time series model until unless we remove that, either we remove the missing observations or we fill that missing observation. So to examine that whether it is a missing observation is there or not, so the function is basically is dot na data. So let us say if I am writing here is na, then data here. So basically if we execute this, what we get the result of in the logical answer here. So for every observation it will give whether there is missing or not. If there is the missing observation, then it will result in the true. So for all of the series, for all of the observations we have to observe. But there is a better way to do that. Rather than using is na data, we can use the function sum. So when you use the function sum before this, basically it will tell you how many missing observations are there. So let us execute this. So once we execute, it shows 0. That means there is 0 observation missing. So that means there is no missing observations we have. Then next, these things already we have discussed earlier. So here basically when we use the hat, so basically it will show the first 6 observations. Similarly, if we are using tail, it will show us the last 6 observations. So these things basically is to make sure the data has been imported properly. Then using the summary command, which is in the base, that means base R, that means we do not have to install any packages to use the summary command. So if you are using this, so it tells us what is the minimum, what is the first quartile, median, mean, third quartile, and what is the maximum of all three. So here, for example, BSE, the minimum value is 23,688, and here the maximum value is basically 80,452. In the call money rate, minimum is 3.136 and the maximum is 6.932. So once we have this, now before using the time series model, before using the time series model, we have to convert the data frame into the time series, and here T data basically here to denoting that the data we have converted into the time series. Then how to convert? We will use the function TS, that is the time series. Then here we give the reference of the data frame. So here we have taken the reference of data frame 2 to 4 because in the first case we have the time. So we don't need that particular first column. So we need the second, third and the fourth column. So here we are recalling only second up to fourth, that is second, third and fourth column. Then here start date, basically we are giving from where it is starting. So here we are using the monthly data. So it is starting from the 2016, the first month. Then the frequency, if it is the monthly data, we have to write the frequency is 12. So we are writing the frequency 12. Now if you click it here, or if we execute this particular command, so what we can observe here, we have another object into the global environment T data, which shows it is a nothing but the time series, and it has from the first observation to 103. So that means 103 observations are there, and there are the 3 variables we have. Then the next important thing is to let's make the plot every series and let us see the behavior of those series. So to plot that, we have ts dot plot, that is the function. Then we are giving uh, the reference of that column and what is the label of x-axis and what is the label of y-axis, and the line width of the plot is 1 and the column is blue. So let us execute this command. So once we execute, so here you can observe the image is here. So if we click on the zoom, so we will have a larger picture of this. So this is nothing but the BSc prices, how it has evolved over the year. Similarly, we can plot the interest rate. Only thing for the interest rate we have changed the color. So this is the weighted call money rate starting from first month January 2016 to December 27th of 2024, and this is how it has been evolved over the years. And similarly, we can plot the CPI indices. By looking the graph, we can guess, we can observe this series seems to be non-stationary. To get it confirmed, we are using the unit root test again here to examine the stationarity of those series. And obviously, there are a lot of different unit roots available. For this class, we are basically limiting ourselves to the ADF, that is the augmented Dickey-Fuller unit root test. To use that, we have already discussed the function is ur.df, then we have the giving the data reference, and here type C basically trend, that we have 3 equations of ADF. So here we are increasing the third equation, that is we are including both the constant plus as well as the trend into the equation. Lags, we are using the Akaike information criteria to choose the maximum lag of the difference. So let us execute this. So if you are executing this, and here is the summary result. So from the summary result, what we can observe, we are concerned with the tau 3. So we are basically concerned with the tau 3 critical values and the first statistic here. So if it is more negative than the tabulated or the critical value, then we will reject the null. Here the null is data is non-stationary. However, what we can observe, this value is not more negative, it is in absolute sense smaller than this. That means we will reject the null. So we are rejecting the hypothesis that the series is stationary. That means we are accepting that the series is non-stationary. So similarly, let us check the other series. So in other series also we are looking the same inference, and similarly for the third variable we are also getting the same inference. So that means all 3 variables are non-stationary at the level. Then what we are doing here, you need to with a structural break. Though we have not discussed in the theoretical classes about the structural break. So we know that if there is the structural break, literature suggests that if you are using the unit root in presence of the structural break, then the result will be misleading. So for example, let us say if you are looking this graph of the call money, weighted call money rate. So here from here you can see there is a sudden jump, and here again there is the sudden jump. So this kind of sudden change is the structural break, which we have discussed in the few introductory classes. So in presence of such structure, the unit root test, basically the traditional unit root test, which does not take account of the structural break, the results might be misleading. So to avoid that, we have used the test which is again available in the URCA package, that is the Andrews-Hewitt test with the one structural break. So we are using this. So here what we can see, the result is this. Though the statistics has improved, still we can confirm that the series is non-stationary. However, it is very close to the critical value, and it is an interest rate. So, here we are considering that, let us assume it as a stationary process. So, once it is a once those series which are the non-stationary, what we have to do, we have to make the stationary. How we will make the stationary? By the differencing. So, here we are differencing those series which is non-stationary. So, basically the difference is the function, and after differencing we are storing the data into dt data. Now, here we have t data, then we are giving the reference. Here reference you can see it is -2. Basically -2 means I am asking R to take the difference of every column present here except the 2. So, that means I am asking to take the difference of the first column and the third column, but not the second column. For that we have written the -2. Okay, that leaving that column you take the difference of all other columns. So, if you run here, so we are getting here. So, if you click here, what we have only 2 columns. The third, the column representing the weighted column money rate is not there because we have not taken the difference of that. So, now here basically we are renaming those series. So, RBAC, because we have taken the difference, now it is nothing but the return. So, we are naming as RBSE. CPI is now nothing but the inflation, we are taking the inflation. Interest rate here as usual we are keeping the same because we have not taken the difference of that. However, while we are taking the difference, we lose the first observation. But for the weighted column money rate, since we have not taken the difference, the first observation will be there. So, to bring all the columns to have the equal number of observations, we are deleting the first observations here. So, I am asking take the interest rate, but excluding the first observation. So, that is what basically we are doing. So, now you can see here we have these 3 variables. So, once we have these 3 variables, now we are combining that to create a time series data in one. So, for that we have used the function cbind and combining these all 3 columns. So, once we combine, we can see here we have this W data, where basically I have used the W basically to show that working data. So, now we have cleaned the data, we have made the data ready to be used for the vector autoregression. So, here now we have all the 3 series here in. Now, we will be using this data for our analysis. So, again let us see the certain things about the data. So, head, so we can see the first few observations of this data, and the start, what is the starting date? Starting date is the 2016 2, that means February 2016, because while differencing we have lost the January data. And what is the end? End is the 7th month of the year 2024. So, let us now plot the difference data here. So, if you see here the difference data is plotting looks like this. So, we can make the inference the series are now stationary. So, then the first step in the vector autoregression, as we have discussed, is to finding out the optimal lag to be used the system. So, for that we use the function var select. So, remember here var select is function from the variance package, where you have to write the VAR in the capital, then the select, then we are giving the reference of the data, then the maximum lag, how much you allow to have. Type both here is basically we are including both constant and trend into the equation of the vector autoregression here. So, if you execute this, so what we have the lag selection. So, this so we are executing this and storing the result into the lag selection object we have created. So once we write the lag selection here and execute, we get the result here. So what you can observe here, what we have given the maximum lag. Maximum lag is 10, and here the 4 criteria is there: AIC, archaic information criteria, HQ hand quanon, SC is the SWOT information criteria, FP is the final prediction error. Then out of that, what will be the optimal lag? So for any criteria of this, any information criteria, the lag which have the minimum value will be treated as the optimal lag. Now let us say, for example, AIC, in the first observation what we have 11.592, in the second 11.35, third is 11.31, again fourth is 11.32, and 5 is again 11.43, 6 is 11.454, 7th is 11.41, 8 is 11.47, 9 is 11.51, and 10 is 11.36. So if we compare all the 10 AIC of all the 10 lags, so minimum we are getting at the third. So here we are getting the minimum at the third lag. So that means according to AIC, the optimal lag will be 3. So that basically here we are asking to do that. We are creating an object optimal lag where we are storing that lag selection, that is selection of the first. So we are asking select the optimal lag based on the first criteria from the result which we have stored into the lag selection. So if we execute this command and print optimal lag, what we can see, it is nothing but the 3. So the lag which have the minimum value of AIC has been selected as an optimal lag. Then the next step is estimation. So here we are using the estimation here. So here the var model, again we have created an object by the name of var model, where basically we will be storing the results of the vector autoregression. Now to execute, to run the var, what we need a command var, that is the vector autoregression here. Then the working data, so that means the reference of the data frame. Here P, that is the lag of the vector autoregression, that we have assumed it should be optimal lag from here. Type, again whether you wanted to include both constant plus trend or only variable, constant or. So you can see here type we have constant, trend, both, and none. Then seasonality, seasonal component we have, or we have any exogenous variables or not. So maximum lag and the information criteria which we are going to. So based on this information criteria, here we have already choose the optimal lag, so there is no need to do that. So here we have the both, so we can use either both, constant, depending on which kind of model we have. So let us execute this here. Then summary is again to find out the print of the results. So what kind of result we have printed here? So if we see here, so here the vector autoregression estimation results. So the first part, it says endogenous variables. We have already discussed in the vector autoregression, every variable is treated as the endogenous variable. So RBAC, interest rate, inflation, all three are considered as the endogenous variable. Deterministic variable, both means constant as well as the trend. Sample size, log likelihood, all other informations are there. Now estimation results. So estimation result, this is the first equation, that is RBAC depends on the lag of its own, lag of the interest rate, lag of inflation, then the second lag of its own, second lag of interest, second lag of inflation, similarly up to the third lag. And we have also constant plus trend here in this equation. So this is the first equation of the system. Similarly, we have the second equation. So before that, these are the significant. So wherever we have star, those are the significant we have. Then we have the residuals, adjusted R square, multiple R square, everything we have. Then similarly, we have the estimation result of the second equation and the third equation. And at the last, we have variance and covariance matrix, and we have correlation matrix of the residuals. So once we estimated the where, then what we have to do? We have to find out the different diagnostic tests or results. So the first thing, we are plotting the residuals of a particular equation. So let us plot the residuals of the equation interest, that is interest is the dependent variable here we have. Again, to using the same the plot, then we have to give the reference of the estimated model, that is the where model, and names is the basically for this particular variable we wanted to find out or plot the estimated residual. So if we are using this, so here we can see, so basically it's plot new figure margins too large, that means it will not be able to adjust here. So if you see here, so what we have uh, this fit and the residuals, and this is the residual series. So by looking this graph, we can observe that yes, it seems quite a good fit here. So apart from that, so if you the error of this figure margins too large is basically when the figure is larger than the available pan. So in that case, we have the two solutions. Either we can increase the pan size of this, or we can have a command before this. So the command will be this bar, then giving the margin 1 1. So here basically we are fixing the margin manually. So either we can expand this, or we, in some of the cases you may not get this result. Here we are getting if the window is very small. So let us rerun this. So if we are rerunning this, so here we can see this particular result. So this plot of where model with a specific variable, a specific equation, what it gives us? It gives us the fit and the rigid, the diagram of the fit and the actual observation of interest rate. So here we can say the estimated and this has quite fit. Then we have the second column. So here the second layer, that is the basically error, how it has plotted observed years. Then we have the ACF and the PACF. In case of ACF, what we can observe, it like 0 only we have non-zero autocorrelation, otherwise for all everything it is 0. And similarly for the PACF, it is basically we have. So what this, from this graph we can infer? From this graph we can infer the estimated residuals is stationary. So now let us check the other diagnostic test here. So first, from this graph, let us see the serial autocorrelation here. So if you print the serial test, so for the autocorrelation test, what we are using the serial dot test, that is the function. Then we have to give the reference of the estimated model. Then we have to give the what is the maximum lag we have here. Then type basically asymptotic. So there is the two types. One is the asymptotic. Asymptotic when we use when we have the large sample size. So here we have enough data, so we are using the asymptotic. So if we execute this command, so all the result of the serial autocorrelation has been stored into the serial underscore test object. Now let us print that. So here basically I am printing that. So here what we are getting, the portmanteau test of this wire model. So the residuals of this. So here what we can see, the chi-square is T4.2 and p-value is 0.03. Remember, this is not only for the residual of interest, this is the residuals of the whole system. So in that case, it seems there is the presence of autocorrelation, as we are not able to reject the null hypothesis. So though at the 10 more than at the 5% we can reject this. Now, so ultimately what we can conclude, there is no presence of autocorrelation. Similarly, we can test for the normality. So for the normality here, basically you are using the function normality dot test, and we are giving the reference of the estimated model and storing that result again into the an object named as norm or norm1. So if you execute this, so here we are getting this result. So remember here, this is the basically by default giving us the multivariate uh, normality test. So here what we can see, this multivariate normality test, that JB multivariate normality test, where what we have p value which is basically 2.2 e minus 16 is basically a very small number, because we know that e minus 16 is nothing 2.2 multiplied by 10 to the power minus 16. So it is a very small number we have. So p value is very close to 0, so that we will reject the null, that the residuals are normal. Then we have skewness only and kurtosis only. So here the same thing we have repeated this result. Similarly, we can have the arch effect. So here we are looking the arch effect of this. So to see the arch effect, we have arch dot test. So if we execute this particular command and storing the results in the arch1 object and printing that, we have the arch effect. So here we can again we have arch effect of the multivariate form. So in case of the multivariate form, here we can observe the result. So this is the result basically we are getting. So it seems there is the presence of heteroscedasticity. We can plot the results also. So let us plot the results of for the particular series, that is the interest rate. So we wanted to plot the arch effect of the residuals is estimated for the equation of interest rate. So if you are plotting that, so what we got here, we have got this. So this is the residuals of interest rate, and this is the ACF and the PACF of those. So if we zoom it here, so here we can see these are the basically ACF and PACF, and here we have the histogram. This. So by looking, it seems the data, the residual of for the interest rate is quite good. It almost follows the normal distribution, and here it is in stationary. So this was about for a particular specific equation. Similarly, we can have the specific equation. For example, we can have the equation of the return BSC, or we can have the equation for the inflation as well. Then, as we have discussed in the theory classes, that we need the parameter stability for the vector autoregression model. So here we are using the function stability to examine the parameter stability of VAR model, and type here OLS Kusum we are using. There is the two different methods. So often we use the OLS Kusum method to examine the stability. So storing the result into the object tab, and here we are plotting. So if you plot it here, this is the basically plot we are getting. So for every equation here, you can see for the equation of return BSC, for the equation of interest rate, and for the equation of inflation. In every equation, we can see these are basically within the error bars. That means the parameters of this what estimated vector autoregression model is stable over the period of time, over the sample. So these are the diagnostics. So from this diagnostic test, what can confirm that estimated model seems good. So once it is good, now let us interpret the results. As we have discussed in the vector autoregression, it is not easy or desirable to use the coefficient for making the inference. So what we use the two options, that is the impulse response function and the variance decomposition function for making the inference. So here basically we are using the first impulse response function. For the impulse response function, we use the function IRF, then the VAR model. So that is the estimated model. N ahead, that is for how many horizon we wanted to have the impulse response function. Response, see there are the two things we have impulse and the response command into the two arguments we will having in the impulse response function, that is response as well as the impulse. Impulse basically the shock to the particular variable. Response basically how that particular variable reacts to the shocks to the different variable or its own shock. So the response basically reaction to the shock, impulse is basically giving a shock. Now for example here I am written the response is equal to return of BAC. That means I wanted to see the response of return only the series. However, I have not written anything about the impulse. That means impulse default. Default is that it will give the shock to the all three variables. However, here we are limiting the response to examine the response of only one variable. If you don't write the impulse or the response, that means you wanted to give the shock to all three and you wanted to see the response of all three. So let us store that result here in IRF and plot it. This boot argument is basically for the creating the standard error for this IRF. So if we are executing this and plotting this, so what we have here, we have the observation. So this is the orthogonal impulse response from the RBAC to the RBAC. So this is the first. Okay, the response of the return due to the shock to the RBAC. So what we can inform from here, as given a shock to the return to the BAC sensec, so it starts decreasing and further decreasing, then the effect becomes 0 at the 5th month. So till 5th month there will be impact of the shock here. Now see here what we have, hit return to see the next plot, because what we have seen the response of RBAC only to the shock of the itself. So what about others? To get the plot of others, what we have to hit the enter button. Then here we can see now the response of RBC giving the impulse response to the interest rate. That shock we have given the interest rate, then how return this RBAC reacts. So you can see here for the it increases, then it start decreasing, and ultimately at the month of 7th the effect becomes 0. So this is basically shows the dynamic reaction response of the return by giving shock to the interest rate. And here again if we hit the again, so what we got the response of the RBAC in when we give the shock to the inflation. So here what we see, when there is the one standard deviation, that is the one positive shock is there in the inflation, the return will increase, then further it declines and ultimately goes up to the, even after the 10 horizon there is the some impact is there. So that's how we capture or we analyze how the other variables in the system will react given a shock here. So let us see the second situation where basically we wanted to see the impulse response from the interest rate to the response. So that means we are giving only shock to the interest rate and we wanted to see the response of only one variable, that is the return. So here we can see we have the similar shock. So there is no option of hitting return because we have restricted. I am giving a shock only to the interest rate and we wanted to see the reaction only of the return. So that's how we can observe here. Then the second tool to examine the second tool for explanation is the variance decomposition. So what is the variance decomposition? Variance decomposition we have already discussed. It shows that how much percentage of the variation of a particular variable is due to the shock of the different variables. That's what we call the variance decomposition. So for the variance decomposition, what we do, we use the function FEVT, that is the forecast error variance decomposition, where we give the estimated reference of the estimated var model, then for how many period we wanted to that. Then here again I am storing the result in the FEVD result. So let us execute this here. Then let us print. So once we do print, so what we can observe here, this is the first 10 variance decomposition of this. So when we are giving a saw to the RBAC, then how the others basically it reacts. Similarly, due to the interest rate, how the others observing, and similarly for the inflation, how the others react here. And it is better to see that in form of plot. So if we plot this, here we got this particular graph. So from this graph, what we can observe, if we see the first graph, that is the forecast area variance decomposition of the RBSE. So here we have the RBSE. So in that case, what can we observe? If you see the first leg here, in case of the first leg, it is only showing the black color. That is, all the variations in the first leg is due to itself. As we move here, we can see here, for example, third, there is the little line of the this color, that is inflation. That means out of the total 100% variation in the return, this much is for its own shock and this remaining is due to the inflation. Here we can see as we move past, then here we can see more and more effect of the inflation. So this much is explained by the inflation variation and this much is explained by the its own variation. Similarly, we can see for the other, for example, in case of interest rate, similar story we have here, that in the first leg, if you observe that most of the variation is due to inflation, but some of the variation is due to the return of the BSE Sensex. However, as time passes, we can see the impact of this return is becoming less and less, but the speed of is very less. However, as we move here, the impact of inflation is also observed for the interest rate. So that means the variation in interest rate is largely explained by its own variation. However, the certain percentage do also explained by the interest rate as well as the BSE return. Then the last, what we can see, the how much contribution of other variables we have in the variance of inflation. So here we can observe again in the variation of inflation, the largely it is basically of its own, and others have as lag passes, the effect of other variation do have impact on that. Now, so this was about the where. However, what we have discussed, if the series are non-stationary, then in that case, and they are cointegrated, in that case, rather than losing one observation, by differentiating it, we can estimate a vector auto error correction model at the level, then we can go back and we use the where. So that's what basically we are doing now here. So first what we have to do, we have to check whether data is stationary or non-stationary, which already we have checked and we have found that data is non-stationary. Then the second, we have to test whether both this series there is the cointegration. If there is the cointegration, then only we will go to the vector error correction model. So here I am using the Johansson test for this examining the cointegration among this variable. So let us see this particular command here. So what we have this. So for the Johansson cointegration test, what we have the command here, this ca.jo. Now here see, we are giving the reference of T data, which is basically, if you remember, is the non-stationary data. Then the second is type. Second argument is type. Type is basically, there are the two statistics we can use to examine whether there is a cointegration or not. One is the trace statistics, another is the maximum eigenvalue statistics. Then here K is nothing but the lag of the equation. And here EC date is basically whether we wanted to include the constant or trend or both into our regression equation here. So here you are using the constant only. Then here the another argument we have spec, that basically shows whether we have transitory or no. So if you see here in this case transitory, there we have the two. One we have the long run, we have the another we have transitory. Long run basically we wanted to see the combined effect, where in the transitory we are basically in the short run. So we have this. So let us execute this and see the summary result here. So if you can see in the console, so what we see, here we are seeing that this will be the result of the Johansson procedure. However, we are concerned of about this part only, this much only. So what is basically here? Here the null hypothesis, there is no configuration vector, and here is the t statistics, and here this is the 10% critical value, this is the 5% critical value, and this is the 1% critical value. If this calculated 32.43 statistics test statistic is more than of any of this critical value, will reject the null. Here the null is there is no configuration. So what we can observe here, this is 32.43 and the 10% critical value is 32. So that means we are rejecting at the 10% level of significance. Then we move to the second. So here the null is configurative vector is 1 or more than 1. So now let us see the test statistic. What we have 13.81, all others is basically larger than this. That means we are not able to reject the null. So here the null is there is one configurating vector. So by looking this result, what we can conclude, there is the one configurating vector. So that is there is the configuration among these three variables we have. So once we have configuration, and the second already we have seen that these are data are non-static. That means we will be able to use the vector error correction model. So to use that, what we have this particular function KJORLS. And this is the function to estimate the VECM. Here what we have Johansson test, that is the contract vector which we have stored here, and here we have giving R is equal to 1, specify the based on the configuration rank. So we have already 1, so this is 1, and here is this the configuration test result we have stored here. Now we using this to estimate a VECM estimation. So let us say here the VECM estimation we are estimating, and this is the summary result. However, we are not concerned with that. Now what we have to do, from VECM we wanted to go to the back to the vector auto regression so that we can make the inferences. So let us do this. So if we see, you wanted to see this results of this model, one, this. So here we can see the result of this coefficient matrix log, endogenous variables, everything is there. So however, we know that we do not use the coefficient to make the inference. So let us take the inference of IRF. So we are using the IRF, same here. Let us plot this. So here we can see the plot of this IRF BAC in response of BAC. And if we hit enter, we can see the response of weighted colony rate. So basically response of the BAC while giving the shock to the weighted colony rate. And if we see the other, that is the response of BAC while giving the shock to the inflation. Similarly, we can use the variance decomposition here. So this we have the variance decomposition here. So basically in this class we have discussed how we can estimate a vector autoregression model, how we can estimate the VECM model, and how we get the inference from such results. So thank you so much. So whatever we have discussed in the multivariate time series analysis, we have implemented those using the R. See you in the next class. Hope you are enjoying the class. Thank you so much.